The current predominant battery energy storage technology for electric vehicle is the lithium-ion battery. Now, the batteries are fundamentally a storage medium made up of two electrodes dipped in a electrolyte. Now, this electrolyte provides a medium for the exchange of ions, which in turn produces the electricity. Each of the battery chemistry, which are discussed in the previous slide, has their own unique advantages and disadvantages. Although the innovations in lithium-ion batteries have propelled them to become the market leader for use of the most handheld and portable devices such as our mobile phones and laptops, as well as they are used in electric vehicles as well. Now, this is primarily due to their specific energy. So, whatever the watt hour per kg term they have, their cycle life, and the higher efficiencies. And as I said earlier as well, there is nothing such as a perfect battery, right? So, lithium ion also do have some downsides, which include their higher cost and the need of a very complex safety and monitoring system. So, which in turn you need a battery management system in order to take the most out of from the lithium ion batteries. Now, in the next slide, in general, lithium-ion batteries can be characterized as an energy storage system that rely on insertion of reactions from both the electrode ends. Okay, so then now the lithium-ion act as a charge carrier, which will carry the charge from either negative to positive or positive to negative based on what it is performing, whether it's charging or whether it's discharging. Now, this is a broad definition of the lithium ion, and under this definition, there are several different cell chemistries that make up of the lithium ion battery families. And among these lithium ion batteries, most of them use a negative electrode, principally made up of carbon, for example, the graphite. Now, and the electrolytes used varies based on the choice of electrode materials, but is typically composed of a mixture of lithium salts. An organic solvent and a mixture of lithium salts. A separating membrane is used to allow lithium ions to pass between the electrodes while preparing an internal, while the same separating membrane also prevents an internal short circuit. Now, I have tried to explain the same thing using this diagram. Here the battery is operating as an energy source, which means we are using the battery and we are withdrawing the energy from it. So you can say the battery is in discharging state. Now, the electrons will travel from the negative electrode to the positive electrode, while simultaneously lithium ions travel from the negative electrode through the electrolyte to the positive electrode to maintain the electro neutrality. Now, this is the phenomena where the electricity is being generated. Okay. Now, when the system is operated in charge mode, that is, you can say an electrolytic device, the electron current and the lithium ion flow is reversed. Now, this diagram represents a discharge, and when we go for charging mode, then the direction flow for electron current and the lithium ions will be reversed. That's it. Okay. So now let's move on to the different positive electrodes. Now, positive electrodes generally are intercalation compounds, now usually from which the lithium positive ions are diffused out or they are back in. Okay, so the few of the well-known examples of this material used I have listed here. Generally, the choice of the material is predicated on the desire of the battery performance. So, for example, how much you need the energy versus power, or how much life cycle you want, or what should be the lifetime of the battery, or is it this chemistry safe or not, and ultimately comes down to the cost as well. Okay, so we are going to look at each one of these positive electrodes one by one. So we'll start with the lithium cobalt oxide. Now, this lithium cobalt oxide was first developed by Sony in 1991. Now, this lithium cobalt batteries are very reactive, and therefore they suffer from a very poor thermal stability, and that's why they must be monitored during operation to ensure the safe use. Now, again, the cobalt is present in a limited cobalt is not very abundant in the nature. Its supply is limited. That's why the limited availability of cobalt makes it more expensive and difficult to be a viable option to use in case of the EVs. So when we talk about when you want to use electric vehicles, you're talking about very large size batteries, and if we start to use cobalt in that much manner, then ultimately we will run out of cobalt in some point of time. Nevertheless, This high energy density battery was used to power the Tesla Roadster, the first generation one. Okay, now let's move on to the next chemistry, which is lithium nickel oxide. Now this lithium nickel oxide, it was recognized as a promising material for high voltage batteries, specifically because it had a, if you remember from the previous slides, I discussed about how lithium ions have a average nominal voltage about 3 volt or something. Now this lithium nickel oxide had a nominal voltage of 4 plus or maybe 4.2 volts or something. That's why they were looked as a very promising material, but they come with their own difficulties, especially the formation of the self passivation layer. Now this self passivation layer is nothing but it will create another protective layer over itself. So this caused with multiple difficulties with the use, because you're trying to charge and discharge the battery packs, and this self passivation layer will prevent the ease of use. So that's why then lithium nickel oxides were not, like, they didn't gain that potential for that thing, but because of this lithium nickel oxide, they contributed for the research and development of NMCs, which is the next class which we will look at, lithium nickel manganese cobalt oxides. Okay, so before we move on to the NMCs, I want to discuss about the lithium manganese oxides first. So this architecture forms a three-dimensional spinal structure that will theoretically that improve the flow of the electrode, and with the increase in the flow of electro ions, now we have a lower internal resistance and also improved current handling. What this means is this will have a lower internal cell resistance, and this will enable the battery pack to fast charge and also at a very high current discharge. So whenever you need now high current discharge directly relates to specific power, so you have more power, a more instantaneous power, I must say. So this lithium manganese it was possible for these lithium manganese to be discharged at the current of 20 to 30 amps. Also they will have a very moderate heat buildup, so we are not very much worried about the heat generation as well, which we will look at. Okay, so now this chemistry provided a better thermal stability than the previous ones like lithium cobalt oxide batteries, but at the same time they resulted in a lower capacity, which approximately 33% lower capacity compared to the LCO or lithium cobalt oxides. And also the lithium manganese oxides had a lower lifespan when compared to the previous chemistries. Now most of these lithium manganese batteries will blend with the lithium manganese cobalt oxides, or as I said, NMC. Now this will improve the specific energy and prolong the lifespan. How it is done, we will see when we are going to study about the lithium manganese cobalt oxides, or NMCs. Okay, now this LMO, or we can say lithium manganese oxide, and NMC have been used in multiple EV manufacturers. They are combined, and we'll talk about the fusion later on, but they have been used by the multiple manufacturers in the past, including the very famous Nissan Leaf, Chevy Volt, and BMW i3. Now the next chemistry which we want to look at is lithium iron phosphate, or LiFePO4, also commonly known as LFP. Now the LFP will offer a very good electrochemical performance with low resistance. At the same time, it will provide high current rating and long cycle lives. Now this LFP will help to stabilize, or the phosphate present in the LFP will help to stabilize the electrode against the overcharging and provides a higher tolerance to heat, which means that these batteries are not very prone for thermal runaways, and which usually are the reason for the recent batteries catching fires, right? So why this happens? Because if you have a higher tolerance to heat, which means that you limit the breakdown of the material, ultimately prolonging its life. So this LFP had now LFPs have a higher self discharge when you compared with the lithium ion batteries. Now this is a one of the issue, because now you need to have balancing issues. Now if you have a higher self discharge, which means in very frequent times you have to balance these cells. Now cell balancing, which is a term of a battery management system, where you try to balance out the capacities, be it voltage, be it the available capacity. You try to balance it out with the across the battery pack. As I said, cell is the smallest individual unit, and the battery pack is the combination or the multiple cells combined together. So you have to balance these cells. Okay, so that's the one problem with the lithium iron phosphate, but this is possible, or you can just simply mitigate these issues if you use a very sophisticated electronics. Now with the advent of the electronics and power electronic devices, which is nowadays, it's very much possible to do so. And even though it increases the battery pack cost, but still the longer life cycle, higher current rating, and the higher tolerance to the heat are the very much advantages which we can go for. And at the same time, they provide a very efficient power to weight ratio, and as I said, the previous one, the higher safety features, and its chemistry is typically have a resistance for thermal runaways. So that's probably the reason nowadays the lithium iron phosphate are achieving a very great popularity. Okay, now the next chemistry which we want to look at is lithium nickel manganese cobalt oxide, or in the short form NMC. Now these electrodes can be designed for a very high specific energy or power with high density. Okay, now the secret for the NMC lies in the combining the nickel and manganese. Okay, if you remember from the just a few slides back, we talked about lithium manganese oxide and lithium nickel oxide. Now just assume that you are trying to mix both of these chemistries. Now how this becomes a very win-win situation is, nickel is known for its high specific energy, but at the same time it has a poor stability. Now manganese will have the manganese benefits from forming a spinel structure. Now that spinal structure allows for a lower internal resistance, but at the same time it will offer a low specific energy. Now just assume that you are trying to combine both goods. So you are trying to combine nickel and manganese, and this, what it will do is, it will enhance each other's strengths. That's why this will ultimately make the NMC the most successful lithium ion system yet, and it is very suitable for EV powertrains. LFP is there, but NMC is better. You can say you're trying to maximize both potential from the nickel and manganese in case of the NMCs. Okay. Now the next one is the lithium nickel cobalt aluminum oxide. Okay, or NCA, we can in the short term we can call it as NCA. Now these NCA share a very similarity with NMCs. They also offer a very high specific energy and specific power, and as well as the long lifespan. But NCAs are not as safe as when you compared with the previously mentioned chemistries, and they also require special safety monitoring systems, and after that only they can be used inside the EVs. Okay, so yeah, so we are done with the positive electrodes here, and now we will move towards the negative electrode sides. So there are basically two main types of negative electrodes which are like very popularly being used. One is lithium titanate and the other one is the carbon based electrodes. There are certain few new types of electrodes under development, such as lithium metal and lithium metal alloys, and they specifically focus towards lithium silicon alloys, you can say, or the conversion electrodes, but most of them are still under development. That's why we use mainly two types, which are lithium titanate and the carbon based electrodes. Now let's go for the first one. So the very first one is the carbon based electrodes. Now these carbon based electrodes will usually, as the name suggests, they have carbon and usually a synthetic graphite. So now still this is the very popular choice. Why so? Because of its very high specific capacity, its high round trip energy efficiency, as well as since graphite or the carbon based electrodes or the whatever material they use, this synthetic graphite, that's very abundant in the nature. It is very low cost, and at the same time it's a non-toxic material. So ultimately this will become a very popular choice. It's a very good choice for electrodes, and therefore it's widely used among the lithium ion batteries. However, they're under some specific conditions. Now they are not very reluctant with the atmospheric oxygens. So in case these carbon comes in contact with the atmospheric oxygen, or in case of a thermal runaway event, these electrodes can catch fire. So you have to be very careful with the construction of a battery pack if you're using lithium carbon based electrodes in the lithium ions. Then the next one is the lithium titanate. Now the lithium titanate was designed to replace the graphite in the negative electrode of any typical lithium ion battery, since graphite was a very popular choice earlier, and just because of the electrode catching fire, there was a need of another very safe negative electrode, which came in the form of lithium titanate. And again, this had a spinel structure. Now you must be now familiar with the spinel structure. What spinel structure does is it will lower the internal resistances, right? So yeah, and then for lithium titanate you are using a counter electrode, which is lithium manganese oxide or NMC. Now due to their high level of safety, these lithium titanate based batteries are used in mobile medical devices, because they are a little bit costly at the moment, but at the same time they are very safe. So that's the reason, obvious reason we use them in the mobile medical devices. Now let's come to the next negative electrode, which is a lithium metal. Now, as if you remember from the earlier slides, lithium metal is a potential, it has the potential but still under development. So yeah, so we'll just take a broad look at what lithium metal is. Now lithium metals, they provide a very large capacity and the lowest negative electrochemical potential among these the above mentioned ones, the carbon based ones and the lithium titanates. But yeah, obviously they are very strong contenders for that because of this very same regions, but they have significantly higher electrode capacity, and and why they are very much desired is because if you have a very higher electrode capacity, which means you can decrease the weight or the mass of that electrode, which will in turn decrease the mass of the overall battery, and some scientists claim that it is about a third of the overall battery. So but now seems very good. Lithium metal comes out to be a very strong or very desired candidate, but unfortunately lithium metal electrodes in the secondary batteries, whatever research or experiments have been conducted, they have been proved to be very challenging because of the growth of metallic dendrites, and these dendrites will short circuit and then lead to a thermal runaway, and which will intend risk for a fire or even explosion as well. So nevertheless, lithium metal surely has a potential. Research is going on in this way. So now obviously we need better negative electrodes. We had a very decent run with the positive electrode options. Now we are looking for the negative electrode ones. So research in this field is going on, and there are multiple attempts to create a safe lithium metal electrode, and if the research eventually we will have a more practical, a greatly enhanced and a better negative electrode, and this will in turn enhance the performance of electric vehicles or our general EVs. Okay, so obviously if you're decreasing the mass of the overall battery pack about a third, which means you can either carry more battery at the same available mass, or you can carry you can make lighter vehicles, which in turn improve the performance, be it acceleration or be it range as well. Yeah, so now the third one, we looked about positive electrodes, negative electrodes. Now let's look about electrolytes. Electrolytes, they are also a very essential part of the battery, and they provide the ionic conductivity, which eventually enables the lithium ions to shuttle between two electrodes. So that movement of travel, you can say, is provided by the electrolyte only. While they are not electronically conductive, there are two major classes of electrolytes exist, one being liquid, you can say aqueous or organic, and the other one being solid, which are polymer and ceramic. So let's look at the one by one again. The very first one is the aqueous electrolytes. Now aqueous electrolytes you can refer to directly from the lead acid ones as well. So they too have a liquid aqueous electrolytes where the water is present. Although these aqueous electrolytes conceptually are safer and have lower potential environmental impacts when you compare with the other ones, but they will ultimately restrict the electrochemical voltage window. So you want higher voltage window to use less cells, right? You remember that if say for example if you have to use a 100-volt system, then you have to, like, if your restricted electrochemical voltage window is only 1 volts, which means you have to have 100 cells in series, and they are not very good for the capacity, so capacity remains the same. But for example, if you have a higher electrochemical voltage window, say for example 3, which means now you are using 3 for every 3 volt you are using 2 less batteries, which you ultimately use to increase the capacity. So there have been multiple attempts to increase the chemical window, but none of it have yet to be commercialized. So they are all them in the research and development phases. The next one will be the organic liquid electrolytes. Now, in order to achieve a wider electrochemical window, lithium-ion battery electrolytes, you can say, they use a organic solvent which is loaded with a lithium salt. Now, if you appropriately blend these two solvents, again this is a very trade secret for the battery manufacturers, the blend, but if you properly blend these solvent and salts, this will create an electrolyte with a good electrochemical stability and with suitably a high lithium ion conductivities, which is obviously needed for a high performance battery. Okay, so the very recent development in this field are you can say something called as the RTIL, or room temperature ionic liquids. Now this mitigates the flammability and volatility of the organic electrolytes issues, but as I said, they are still under research and development. The next class of the electrolytes are the polymer electrolytes. Now, because of the use of an organic liquid electrolyte poses an environmental contamination risk if it is leaked, or it is also comes with the flammability issues, and so now this led to the development of polymer electrolytes, or SPEs. Now they are very promising alternatives to enhance the safety performance of the batteries. Now the composite electrolytes based on the POE, or polyoxyethylene, these have been developed and can have a gel-like structure for gel-like appearance or property for a low molecular weight, or also it can have a solid structure or solid appearance for a higher polymer molecular weight. Now both depending on the what is the application or where it is being used. Now let's move on to the next slide. Now the individual cell designs, they come from several different forms and shapes, and that can be seen in this slide. So you can see we have like cylindrical cells, we have prismatic ones, we have pouch, and we have again the coin ones. So the coin cells or button cells, you say, they are usually present inside your wristwatches or your calculators, or etc. Problem being that that particular chemistry won't allow for recharging very fast, so that's why it is out of question for EVs, electric vehicles. But the first three ones, like the lithium cylinder one, the prismatic one, and the pouch one, now again they have their own advantages and disadvantages for each of them. But when when you study about battery pack, or the structural properties of a battery pack, there you have to keep in mind about which type you want to use. So how is the space available there, and how which type of cooling system you can involve. So based on these factors, you have to choose it. So yeah, at the same time, since this is available in so much different shapes and sizes, this opens up the flexibility and broadens the use of lithium-ion batteries, as they can be literally designed to be around any multiple object form factors, or based on your specific requirements. Now one interesting thing which comes into my mind is, if you look at the nowadays cell phone batteries, now cell phone batteries are again lithium-ion ones only, but they are using two lithium-ion batteries inside one. So L-shaped batteries of iPhones is very popular. So yeah, earlier they used to use a single slab, now they use L-shaped ones in order to utilize the space more efficiently. So that's the beauty of having this much of flexibility. Okay, so moving on to the next slide. And since see literally there is no ideal contender, or there is no perfect battery for electric powertrain, and the lithium ion remains a very good choice for this application. But the major factors considered here are the specific energy, specific power, safety, performance, lifespan, and the cost. Now I'll explain each of these major factors individually. Okay, so this first let's talk about specific energy. Now specific energy demonstrate how much energy a battery can hold per unit of its weight, which ultimately reflects the driving range. Yeah, right. So you have this much of energy, a watt hour, this much of kg. Okay, now per kg rate you can just simply calculate using the math, and then you can ultimately this will reflect the driving range, because it's a closed loop only. You are increasing the battery capacity, you are increasing the battery weight. If you are increasing the battery weight, you are increasing the required traction, which ultimately means you are stuck in an endless loop. So higher specific energy is always good. Then we have specific power, and specific power is nothing but the ability of the battery pack to deliver high current on demand. And you can say that this demonstrates a potential vehicle acceleration. So for example, you can say the launch control present in now the say Porsche Taycan or Tesla Model S or something. So they will have crazy accelerations at the beginning. So that comes from the specific power, or the ability of your battery pack to deliver high current on demand. So overtaking maneuvers, you can say. Yeah. So that's where the specific power comes into play. Then the next one is the safety. Now safety is naturally one of the most important aspects when you are going to choose, when as an engineer you are going to choose a battery for the EV. You want your vehicle to be as safe as possible, because any incident can like damage the reputation of the company, or it can like heavily influence the public opinion. So you don't want to, exactly what you have seen the recent fire incident from battery packs. Yeah, that's where the safety comes in. Now the next one is the performance. Now when I talk about performance, I'm talking about the temperature range. Okay, so what is the minimum temperature your EV can operate, what is the maximum temperature your EV can operate, and in that manner, right? Usually these batteries don't like sub-zero temperatures or very high temperatures, so there is a certain window you want to keep in. But again, as discussed in the previous one, some chemistries allow for a better heat dissipation. Some chemistries are very good with thermal management. Yeah, so that's where you have to make like you have to decide what is the use case where this particular EV is going to be used, and then based on that you can decide upon which chemistry you want to use. Okay, now the next one will be the lifespan. Now lifespan generally reflects about the cycle count and longevity. So how many cycles are cycles, and when we talk about cycles, so say for example a lithium ion can sustain about 200 cycles, which means you can charge and discharge for 200 cycles without losing any intended or the designed capacity or power, right? So exactly that's how your smartphones are even designed. So they just simply take a lithium ion which can sustain around 400 charging and discharging cycles, now which roughly translates to about 1.5 year of use. After 1.5 year of use, you can see already your battery health is being deteriorating, and your smartphone won't hold the charge as long as it was when it was bought or it was new. So they want to change your smartphones. So that's a different topic altogether. But yeah, cycle count and also the longevity as well. So if you are not going to use your electric vehicle for a bit of a period, so that's where the self discharge comes into play. You're not using your electric vehicle, but it's still losing its energy. So yeah, lifespan you have to take in. And the one of the very important thing, cost. So cost again will naturally represent the technology feasibility. So at this moment, which technology is available for cheaper, right? So if you say for example, if you have two choices, if you know that LFP is better, but in your region NMCs are like pretty readily available, and the cost difference becomes a very high thing. So you should be using, or you can say that both have their own compromises, but you can say you are initially intended to design for LFP, but since there is not availability for like at a very cheaper cost, you can go for NMCs as well. So that's how the cost affects your design feasibility. Then obviously you have to incorporate some necessary safety systems, because if you are developing an EV, it is going to be used by a user, it will be on the public road, so you want to have some necessary safety systems. Then obviously you have to add a battery management system to the batteries. As I said, if you are going to use any batteries, they need to be monitored during their operation. So this is done by the battery management system. Also you have to balance it sometimes, again, which is a job of the battery management system. And at the same time, for EV manufacturers, you have to add 8 to 10 year of warranty and all these stuffs, because you want to gain trust from your customers. So that's why you have to show them, we know that this we are providing an 8 to 10 year battery warranty on this battery pack. If anything happens, you can come to us. And these all things are very challenging to like keep the cost down, as well as focus on all of these parameters. Okay, now in this slide I'm going to compare between different types of lithium-ion batteries which are used in the EVs. So I have taken a few of them only here because it won't be possible to show all of them. But these spiderweb diagrams explains that how you can all of the previous factors, as I said. So my major 6 things like specific energy, specific power, safety, performance, lifespan, and the cost, all of them are presented here. And you can see from the diagrams, lithium, nickel, manganese, cobalt, oxide or NMC, lithium iron phosphate LiFePO4, and lithium manganese oxide LMO, they stand out as being the superior among the various candidates. And no wonder we have seen these chemistries on our day-to-day vehicles as well. So yeah, here is a small comparison between different types and their most desirable requirements. Okay, thank you.